what I'd now like to take a brief look at, beginning on page 135, is just to enumerate some of the more common clinical techniques for examining the brain. X-rays. Now, X-rays are when we beam X-rays through the body, but normally X-rays only permit us to see hard, dense structures and not soft tissue structures. In other words, X-rays are commonly used to see if you have a break or fracture in a bone, to see if you have a hole or a cavity in a tooth, but they can't be used to see soft structures. There's something called dual energy subtraction radiology, which uses X-rays of two different wavelengths, and that is analyzed and can be used to visualize soft tissue structures. But what is cerebral angiography? An angiogram is when a radio-opaque contrast medium, such as iodine, is injected into the bloodstream, and as this contrast medium circulates in the bloodstream, it allows us to beam X-rays through the body and see where the blood vessels are. So it allows the visualization of blood vessels. It is used to identify aneurysms. Aneurysms, as we've learned, are bulging weak spots in the walls of blood vessels, arteries, that may potentially rupture or burst, leading to hemorrhaging or bleeding. And the angiogram is also used to identify where there is already bleeding, a hematoma, where blood is coming out of the vessel. What is a CAT scan? CAT is an abbreviation for computerized axial tomography. Sometimes it's just described as a CT scan, where they leave out the word axial. A person is passed into this tube, and X-rays are beamed 360 degrees around that person. If anybody's ever had a CT scan done, you'll see as you move through this tube, there's something spinning or rotating, and it's really an X-ray gun that is shooting X-rays through your entire body 360 degrees. These images are analyzed by a computer, and thus the term computerized axial tomography, and it recreates, the computer recreates serial sections through the body, including through the brain, if you aim it through the head, and that's why it's called tomography. Tome means to cut, as in the word anatomy is to cut up stuff, and you create these graphs or images of cuts or sections through the body, in which, in this case, you could use this to see images of the serial images of the brain. On the next page, 136, so that's what we wrote here. It permits visualizing cross-sections through the body, including the brain, as cross-sectional images are reconstructed. This is used to locate tumors and brain infarctions. An infarct is, of course, dead tissue. So dead tissue in the body, including in the brain. What is a PET scan? PET is an abbreviation of Positron Emission Tomography. This is where a radioactively labeled chemical is injected into the bloodstream. We simply measure where that radioactivity is accumulating in the body. For example, the use of radioactive dopa, a precursor to dopamine, we can see where that dopamine accumulates in which neurons of the brain. So this is used to analyze biochemical processes in the body, including the brain. In this image right here, it looks like the guy is ready to beam up onto a spaceship, but in fact, a radioactively labeled chemical has been introduced into his body, into his bloodstream, and they are picking up or measuring where that radioactivity is accumulating in his brain. PET scans have been used, as it describes here on the lower right, as it describes using radioactive dopamine precursor to see where dopamine accumulates in the brain. Perhaps the single most important method used to evaluate brain and the nervous system is NMR imaging, nuclear magnetic resonance imaging. Commonly they'll leave off the N and just say MRI, magnetic resonance imaging. This method uses very powerful magnets, creating a magnetic field that is turned on and turned off. And in a magnetic field, it causes a lining up of the water molecules in the tissues of the body, because a water molecule is a polar molecule. If you think of water, so the oxygen of the water molecule has a partial negative polarity, and the hydrogens have a partial positive polarity. Thus, it's called a polar molecule, a polar solvent. And in a magnetic field, the water molecule lines up within that magnetic field, a little bit like how iron filings would line up along a magnetic field with a magnet. And when they turn off that magnetic field, the water molecules return back to their original position. And this changing in the position of these water molecules and other dipole substances in the body is used by a computer to reconstruct an image of the body, such as the brain. So we wrote that it permits visualizing internal structure of the body by detecting the distribution and behavior of hydrogen atoms in body structures. This is probably the most commonly used method to visualize the brain and spinal cord and to identify injury to the central nervous system, such as a CVA, cerebrovascular accident, leading to a cerebroinfarction. This is known as a stroke. We then mention electroencephalogram recordings, or EEGs. This is where electrodes are placed on the scalp, on the surface of the head. An electrode is simply a metal contact or a little sticky gel that conducts electrical current, very similar to what's used to record an electrocardiogram of the heart. And this is used to record the sum of all the electrical activity occurring within the brain at any moment in time. So when one records this EEG, you're not recording the action potentials of a single neuron. For that, you would have to insert a microelectrode into an individual neuron. What you're recording is the sum of millions of action potentials that are being generated by neurons throughout the brain. And we know that in different states of consciousness and when there are injuries to the brain, this electrical activity or the wave pattern of these changes. So in fact, on page 137, so 137 here in this picture, it shows electrodes being placed on the surface of the head. These can be used to record the electrical activity of the brain at any moment in time. We see interesting changes in these EEG recordings based on whether the person is awake or asleep. You'll notice that when somebody is awake, they exhibit these very rapid waves. Now, when somebody closes their eyes, you'll notice that the waves become taller in amplitude and they slow down in their frequency. We are very much visual creatures, and a large amount of the electrical activity going on in our brain is affected by the input of signals from our eyes. And the moment we close our eyes, that reduces the input of electrical signals into the brain. You'll notice that when somebody becomes drowsy, the waves slow down even more. And when somebody goes into deep sleep, and deep sleep is what we generally go into early in our sleep cycle, and then later we go into dream sleep. But in deep sleep, the waves become very tall, high in amplitude, and very slow as far as their pattern. Again, suggesting a change in the firing of action potentials in the brain, especially the cerebrum, the cerebral cortex. What's interesting is that as we go to sleep, there will be periods where we have dreams. And when we are in the dream sleep period, the EEG pattern, the wave pattern, again becomes very small waves, low amplitude, and very high frequency, such that it looks almost identical to the EEG pattern that we exhibit when we're awake. So when we're in dream sleep, the brain has a similar kind of activity to when we're awake and our eyes are open. Now, dream sleep is also known as Rem sleep. That stands for rapid eye movement. In fact, if we just come over here in the outline, so in the alert state, when our eyes are open, we have this rapid, low voltage waves. In the sleep state, the non-REM deep sleep are slower, more regular high voltage waves, high amplitude. And with REM sleep, or paradoxical sleep, and this is the dream sleep, why it's sometimes called paradoxical sleep is because paradoxically, even though we're asleep still, the brain wave pattern greatly resembles that of being in the alert state with our eyes open. It's known as REM sleep for rapid eye movement because our eyes are actually moving. So when you have a dream, and in your dream, you imagine looking and you look over here and oh my gosh, there's a monster chasing you. Your eyes actually turn in the direction of where you are in your dream looking towards. You know that when individuals are awakened during dream sleep and asked what's going on, they will report that they were in the middle of experiencing a dream. Now, the vast majority of us, when we wake up in the morning, rarely remember our dreams. The only time really that we're most likely to remember a dream is if we were experiencing a dream right around the time that we woke up. In this diagram right here, this indicates somebody who is sleeping for about 8 hours, and it indicates various physiological changes in their body as well as changes in their EEG pattern. So you'll notice that here it's indicating EOG, the electrooculogram, that's movement of the eyes. The EMG, electromyogram, electrical activity in the skeletal muscles, that's the EMG. And then here it indicates heart rate, and then respiration, breathing rate. And PE does not stand for physical education. It actually stands for penile erection, erection of the penis of a guy. You'll notice that during the first couple, 2 or 3 hours of sleep after you go to bed, you go into that deep sleep, that non-REM deep sleep. And then after a couple of hours of sleep, the brain lightens up a little bit, and the individual experiences REM sleep, rapid eye movement sleep, where they have about 10 minutes of dreaming, as it indicates there, the 10, that's about the number of minutes of that period of REM or dream sleep or paradoxical sleep. During that time, there's increased movement of the eyes, increased tension in the skeletal muscles, the heart rate goes up, the breathing increases, and if you're a guy, very commonly have penile erection. I don't know if that's an indicator of what guys usually dream about, but that commonly happens. Then the individual goes back into deep sleep for about another hour, and then after about another hour, they will lighten up a little bit to this dream sleep and experience about 20 minutes of dream sleep or REM, rapid eye movement sleep, or paradoxical sleep. Again, noticing how increased electrical activity of the eyes as the eyes move, increased tension in the skeletal muscles, increase in heart rate, increase in breathing, and of course, if you're a guy, some more penile erection. As the dream period of sleep progresses, you'll notice that the person doesn't go back into deep sleep, or at least as deep a sleep. In a shorter period of time, return back to that lighter, rapid eye movement, paradoxical sleep, dream sleep, and experience about 30 minutes of dream sleep. And then go back into this deeper sleep, but not as deep as it did during the first few hours, and then lighten up again and have 40 minutes of dream sleep. So you'll notice that the more hours that one sleeps, the more time one is spending dreaming in rapid eye movement or dream sleep. We do most of our deepest sleep during the first 2 or 3 hours of going to sleep. I summarize that right here. The longer you sleep, the more time you spend dreaming in REM sleep. Now, nobody fully understands exactly what's going on in either the deep sleep or the REM dream sleep, but we do know that one must absolutely sleep or one will die. Now, sleeping is not unique to us humans. In fact, all vertebrate animals sleep. Certainly if we think of your dog sleeps, and cats, they're rarely awake. They're sleeping all the time. And even if you have birds, if you have a pet parakeet or a canary, they go to sleep. And even fish will sleep. So this is a common thing that occurs in all vertebrate animals. There is a need to recharge the body and to recharge the nervous system. One of the theories that appeals to me, that doesn't mean it's correct, is that we need to dream in order to edit all the information that we took in over the course of the day. It's almost as if everything that you're seeing, you're making a video recording of in your brain. But you need to file that data so that you can access that data. And during the dream sleep, you're kind of playing back the video and you're editing and splicing and storing that information in your brain to make it more accessible. Now, as you play back this tape of your day or the last couple of days, and you edit it and splice it, it may be edited and spliced with other information, other videos that you've taken previously. And if you happen to be anticipating when you go to sleep taking a really scary physiology exam, perhaps that's, you know that you're a little stressed, and perhaps that gets edited along with your early childhood images of things that are frightening and scary to you, like monsters. So one starts to have dreams of monsters and evil physiology instructors. You'll notice that in this graph, this is a graph indicating one's age. Here it shows a newborn, and then an infant, and a child, an adolescent, an adult, and an old age. And what this is indicating is how many hours a day one sleeps, and of those hours of the day, what proportion of those hours are spent in deep sleep or dream sleep. Now, very interestingly, you'll notice that the newborn, right here at on the far left, where it says a newborn, the newborn is sleeping about 16 hours a day, right? There's 24 hours in the day, and the newborn is sleeping 16 hours a day. Those are the good old days. One was only up for a few hours. You only awakened as an infant, basically just to get more milk, and then go back to sleep again. Now you notice that of the 16 hours a day of sleeping, about 8 hours were spent in non-REM, that's shaded in, 8 hours of deep sleep, and about 8 hours of REM, or dream sleep. And here's an interesting question. What's an infant dreaming about? Their eyes are not yet developed. If you've ever looked at the eyes of a newborn, they do not yet have a fully formed iris. They all have kind of blue-gray eyes. You can't really make out a pupil or an iris very clearly because it's still forming and developing. They have their eyes closed almost all the time. So usually when we think of a dream, we think of a visual dream. So what is an infant dreaming about? And the answer is they're dreaming about the things they are most aware of after being born, and maybe even before birth, and that's touchy, feely, smelly dreams. They are having dreams involving touch and embracing and comforting and smells, odors are the things that especially the infant the newborn is most aware of. This question also arises in an individual who was born blind. So if somebody was born blind, has never seen, they do have dreams, but obviously they are not visual dreams. They are dreams, again, of sounds and touch, because those are the primary sensory modalities that, through which they experience the world. Those of us who are sighted, our primary sensory modality through which we experience the world is largely vision. You'll notice that as one grows older, the amount of deep sleep remains more or less the same, but the amount of time spent in dream sleep decreases. Now, on the theory that dreaming is when we have to edit and splice our visual and other sensory images, our sensory data, so it could be that the newborn and the infant and the child, they are experiencing the entire world. It's all new, and there's so much information that they've got to edit and splice, so they need to devote more time to dreaming. And as we grow older, well, we've seen trees and houses and cars previously, so we don't really have, these are not new experiences that we have to edit that data into our brain. That was only necessary the first time, the first several times that we saw a tree or a house or a car. So perhaps there's lesser need to edit new information as we grow older. Now, the EEG, the electroencephalogram, is not only used to evaluate the state of consciousness or awareness, whether we are awake, whether we're in deep sleep, whether we're in dream sleep, but the EEG is also used to provide information about states of consciousness where it's abnormal, such as in a coma. An individual who is comatose or in a coma state cannot be awakened or aroused. So it's kind of like a permanent state of sleep, probably in most cases due to injury to the brain. EEG is also used to diagnose epilepsy, because in an epileptic seizure, there is an increased electrical activity in the brain associated with very rapid repeating waves. EEGs are also used to identify tumors because the electrical activity is not being generated or transmitted through the brain normally because of this mass that is growing in the brain. And it's used to diagnose various types of injury and damage to the brain. Notice that I did write at the bottom that the EEG, the electroencephalogram, cannot be used to diagnose psychoneurotic disorders, behavioral disorders such as OCD, obsessive-compulsive disorders, phobias or fears such as fear of spiders and fear of snakes, fear of heights. And EEG cannot be used to diagnose what are called panic attacks or post-traumatic stress disorders. These are the most common behavioral or disorders that all of us experience. All of us have some degree of OCD. All of us have fears. Again, the most common would be the spiders and snakes, but everybody has fears of something or other. And occasional panic attacks. These are known behaviorally as psychoneurotic disorders, and those cannot be diagnosed with an EEG. Now, that doesn't mean that there's not a physiological or pathological basis to them. There may be abnormalities in neurotransmitter levels in different parts of the brain, or abnormal wiring in certain parts of the brain, but it doesn't appear or manifest itself by looking at an EEG recording. Let me just summarize by identifying again the three most important methods that are used to evaluate pathologies or injuries to the brain. On page 135, we mentioned a cerebroangiogram, angiography, where a dye is injected into the bloodstream to evaluate blood flow to some part of the body, in this case the brain, and to identify an aneurysm or a hemorrhage in the brain. Secondly, on page 136, we mentioned magnetic resonance imaging, which is used to identify tumors and strokes where there's a cerebral infarction or damage to the brain. And the third was the use of an EEG, an electroencephalogram, which is used to evaluate different types of epilepsy, where there's abnormal electrical activity in the brain, and also used to identify just sleep disorders. All right, I don't tend to emphasize this information on exams, but I think it's all kind of interesting.